Slot-embedded conductor skin effect. A solid copper conductor is placed inside the paramagnetic slot. The conductor carries alternating current of 1 ampere at frequency of 45 Hz. All dimensions are in inches. This example was taken from the paper published by R. Conrad in Transactions on Magnetics, but you may find similar tasks when you design induction motors. When a rotor starts to rotate, the current frequency is high, and the rotor bar impedance is an important parameter that affects the torque value and the start dynamics. We assume that the steel permeability is infinitely high, so we replace the ferromagnetic slot with the boundary condition and set 0 tangential field component at the slot boundary. And we also assume that the field is contained within the slot, so we will set the boundary condition at the top. Okay, let's start QuickField now. In QuickField, I create new problem. Slot. Next. Problem type is AC magnetics. Frequency is 45 Hz. Every simulated device is a three-dimensional object. The slot is long and magnetic field distribution is the same in every and each cross-section. So I can use a two-dimensional model and simulate only a single cross-section. Model class is plane parallel. Length units are millimeters. Finish. On the left, you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. The model is simple, so I'm going to draw it here from sketch. First, I will insert a rectangle with dimensions 18.85 by 8.45. Insert. Then I will insert a smaller rectangle on top of this one with dimensions of 8.95 by 8.55. Insert. That is the copper block. And I will insert another rectangle with dimensions 8.95 by 6.45 on top of this one. So the vertical position is 8.55. Insert. Close, switch to select objects mode, click to select this edge and hit delete button to delete it. Now let's assign labels. To labels, we explain the geometric object's meaning and provide material properties. Again, I am in select objects mode, click to select and type in the label name here. This is copper. This is air. And these edges are the magnetic slot boundary. To select multiple objects at the same time, hold the console button pressed. Okay, this is slot. And this is top of the slot. Now let's provide physical properties for these labels. Double-click the label name in the tree. The relative magnetic permeability of the air is 1. Okay. Relative magnetic permeability of copper is 1, and electrical conductivity is 58 megasiemens per meter. And the total current is 1 ampere. Okay. We assume that the steel slot is infinitely permeable and set their tangential field component on the steel slot boundary. Okay. We also assume that the field is contained within the slot, so the field lines will go parallel to this boundary, top boundary, and I will specify a constant value of electromagnetic potential here, for example 0. Okay. Geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Let's take a look at the results. Here you can see the magnetic field lines and the color map of the current density distribution in the slot. Now let's check some parameters. Remember, we have specified electric current value. How can I check that the current value is correct? I can use the contour tool, click to select the conductor, follow to the integrals, and calculate the integral total current. 1 ampere, and the phase shift was 0 degrees. It's almost 0. And what is the voltage drop? To calculate the voltage drop, I should use the local values tool. Click any point, and here in this point you can get the field parameters: current density, flux density, and the voltage. This is the voltage drop per 1 meter of conductor length. Now, if I would like to calculate the impedance of the conductor, I should divide the complex value of the voltage by the complex value of the total current. QuickField features a wizard that can do math for you. Here it is, impedance wizard. You should select the conductor, and QuickField will divide voltage drop by the current. And here you will get the resistance, inductance, and the impedance. Now let's compare values calculated in QuickField with the values published. Here is the paper. This is the slot. Now let's find some reference value. Here it is. At 45 Hz, the source current density should be this value. Okay, let's calculate the source current density in QuickField. In QuickField, source current density is called external current density. Here is QuickField. I'm going to adjust the field picture and switch on the color map of the external current density. Contour clear. This is root mean square value, and I need the complex value. Again, I will use the local values tool. Click any point You see the current density distribution is uniform, so I can choose any point to click. And here is the external current. Now let's compare these values with the reference. 10,162 and 10,182. The difference is less than 1%, and this is a real component. And what about the imaginary part? 27,327, 27,328. Almost perfect match. Okay, let's change the frequency. For example, 10 Hz. Run the analysis again. Take a look at the results. Again, I will adjust the field picture to make sure that the external current density distribution is uniform. Now let's use the local values tool. Click any point, and here's the external current density. Let's check the values again. 10 Hz, 4,676, 4,672, and the imaginary part 6926, 6937. Again, the difference is less than 1%. If you search for the slot embedded conductor on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.